Assalamualaikum everyone. Before I start today's lesson, I want to think about something. We study electrical and electronic engineering. We learn about voltage, current, transformers, transmission lines, distribution systems, insulation, grounding and communication system. But have you ever noticed something interesting? You do not always need to enter a lab to see electrical engineering. Sometimes you just need to step outside your house. Look at this picture carefully. You have probably seen something like this hundreds of times. Maybe there is a pole like this directly in front of your house. Maybe you pass one every morning on your way to university. Normally, we look at it and see a concrete pole, some wires, a transformer, and maybe a huge maze of black cables, right? Nothing particularly interesting, but wait. Look again. This time, don't look like an ordinary person. Look like an electrical engineer. And don't try to remember anything from your textbook yet. Just observe. Why are some wires placed at the very top of the pole? Why are those wires separated from one another? What are those small components between the wires and the pole? Why can't the wires simply touch the concrete pole? Why is that transformer installed here? And what is happening inside that huge bundle of black cables? Are all of them even carrying electrical power? Interesting, isn't it? A few seconds ago, this looked like an ordinary electrical pole, but now we have several engineering questions hiding inside one ordinary photograph. And that is exactly what makes electrical and electronic engineering interesting. These concepts we study in textbooks are not limited to circuit diagrams, lab, or examination questions. They are open around us every single day. So today we are going to investigate this picture exactly the way an engineer would. For every important part, we will ask 4 simple questions. What is it? How does it work? Why is it needed? Where do we see it in real life? And by the end of this lesson, my goal is very simple. The next time you walk outside your house and see an electrical pole, you will not just see wires and cables, you will see the engineering behind it. Think before I explain. Why are some of these electrical conductors separated by such large distance? Why don't engineers simply put them together? What are these strange ribbed objects? Why do they have this particular shape? Why is there a transformer here? If our fan, television, laptop, chargers and lights need only a few hundred volts, why might electricity arrive in this area at thousands of volts? And if lightning strikes nearby, what protects this equipment? Finally, look at these black cables. Are all of them actually carrying electrical power? Interesting, because what looks like an ordinary pole is actually a small electrical engineering laboratory standing beside the road. Today, instead of memorizing components' name, we are going to investigate this picture like engineers. For every component, we'll think what, why, how, what if, real life. And by the end of this video, you may never look at an electrical pole in the same way again. At first, before identifying individual components, let's understand the complete picture. This pole is supporting part of a local electrical distribution system. But don't think of it as a single piece of equipment. Think of it as a complete system. We can observe equipment associated with electrical conductors, insulators, supporting structures, switching and protection, transformer operation, grounding or earthing and communication network. And here is our first important lesson. Think before I explain. Are all the black cables that we see in this photograph are power cables? The answer is no, not necessarily. Many of bundle cables lower on the pole may belong to communication systems such as telephone, internet, fiber optic communication, cable television, or other low voltage service. So, an electrical engineer should never look at the black cable and immediately say that is power cable. Instead, we ask, where does it come from? Where is it connected? What function does it perform? That is the difference between simply seeing a system and observing like an engineer. Now, why are the conductors so far apart? Look at the upper conductors. Something should immediately make you curious. Why don't engineers simply place all these conductors together? Wouldn't that save space? Think about the wires inside your house. Several wires can travel through the same conduit, so why do overhead conductors need this large physical separation? This answer is surprisingly simple. The empty space between the conductors is itself performing an electrical function. Air is acting as an insulating medium. Many overhead conductors are not covered with thick insulation like ordinary household wires. Therefore, engineers maintain sufficient electrical clearance between energized conductors and between energized conductors and grounded structure. So, physical distance means part of electrical insulation system. Now imagine bringing two conductors at significantly different potentials closer and closer. The electric field in the gap becomes increasingly important. If the electric stresses become high enough to exceed the dielectric strength of the surrounding air, the air can break down. Then an arc may form. Therefore, conductor spacing is not random. It is part of electrical design. Next time you see overhead distribution conductors, don't think, why are they wasting so much space? Instead, think that empty space is actually helping electrically isolate the conductors. Now we have created another engineering problem. The conductor needs mechanical support, but we don't want an energized conductor electrically connected directly to the supporting structure. So we need something very interesting. It must be mechanically strong, but at the same time electrically insulating. What component can perform both jobs? Think before I explain. What are those strange ceramic or polymer looking components attached between the conductors and supporting hardware? It's called insulator. An insulator has two extremely important responsibilities: mechanical support and electrical isolation. Mechanically, it supports or positions the conductor. Electrically, it helps prevent the energized conductor from forming an unintended current path through the supporting structure. But now look carefully at the insulator. Why does it look like that? Why does the insulator have so many ribs? Why isn't the insulator simply a smooth cylinder? Why are there so many ribs or shades? Are they only for decoration? Definitely not. Imagine this pole during a dry period. Dust and pollution accumulate on the surface. Then it rains. Now we have dust, pollution and moisture. The contaminated wet surface can support leakage current, so engineers want to make the surface path between the energized region and the grounded region longer. This surface path is associated with the creepage distance. Now the question arises, what is creepage distance? Creepage distance is the shortest distance measured along the surface of an insulating material between two conductive parts, such as an energized conductor and a grounded support. So remember the key idea: the longer surface path, the greater creepage distance, lower risk of surface leakage and flashover. Now, those strange looking ribs on the insulator suddenly make sense, right? They are not just changing its appearance, they are increasing the distance that leakage current would have to travel along the surface. So, those strange ribs aren't there because somebody thought they looked nice. Their geometry exists because electrical equipment must operate in the real world, and the real world contains rain, dust, pollution and moisture. This is an important lesson. Electrical engineers does not operate inside a perfect circuit diagram, or equipment has to survive outside. Why do we need a transformer here? Now we reach the biggest question in this picture. Inside the nearby building, people may want to switch a fan, use a refrigerator, charge a phone, operate an air conditioner, turn on a television. These appliances do not need thousands of volts. So why don't we distribute electrical energy throughout the entire area directly at approximately 230 or 400 volts? Why use a higher distribution voltage when consumers ultimately need a much lower voltage? Let's answer this with a very simple equation, that is P is equal to V times I. Therefore, we know I is equal to P divided by V. Suppose we want to transfer P is equal to 100 kilowatt. First imagine transforming it at V is equal to 400 volt. Then the current become 250 ampere, right? That's a very large current. Now suppose we transfer the same power, V is equal to 11 kV. Then the current become approximately 9.1 ampere, very small current. Stop here. Compare these two numbers, 250 ampere and then 9.1 ampere. Same power, very different current. Why does that matter? Because conductor loss is approximately P loss is equal to I square R. Notice something very important, current is squared. So increasing current dramatically increase resistive losses. Now let's find the answer. For the same transmitted power, if V increases means I decrease. And because P loss is equal to I square R, lower current can greatly reduce conductor losses. That is one major reason electrical energy is distributed at higher voltage. But now we have created another problem. Higher voltage helps reduce current and losses. That's excellent. But now I have a problem for you. Think before I explain. Can we connect an ordinary ceiling fan directly to an 11 kV distribution line? Can we connect our television directly? What about our phone charger? Of course not. So we need to reduce the voltage before supplying ordinary consumers. And that is where the distribution transformer enters in our story. Conceptually, the distribution transformer acts like a bridge between the medium voltage distribution network and the low voltage consumer network. How does the transformer actually reduce the voltage? Here's another interesting question. Think before I explain. Does the transformer simply burn away the extra voltage as heat? No. Imagine how inefficient that would be. Instead, a transformer operates based on electromagnetic induction. For an ideal transformer, we know V1 divided by V2 is equal to N1 divided by N2. Here, V1 represents the primary voltage, V2 is equal to secondary voltage, N1 represents the number of primary turns and N2 number of secondary turns. For a step-down transformer, N1 is greater than N2, therefore V1 is greater than V2. So, more turns on primary, higher primary voltage, and fewer turns on secondary, lower secondary voltage. Ignoring losses approximately, we can say this. So, when the voltage is stepped down, the current capability on the secondary side correspondingly increases. That's exactly what we need near consumers. Why put the transformer near consumers? Now here's a question students don't always think. Before we reveal the answer, think why not place one transformer very far away and distribute to 230 volt over a huge distance? Remember, P loss is equal to I square R, right? Low voltage distribution generally means higher current for the same power. Also, R is equal to rho L divided by A. Therefore, if conductor length increases, then R also increases. And a simple resistive voltage drop idea is delta V is equal to IR. So, if L value is large, then the R is also increased and the voltage drop also increased. Considering all this, we can say that is the one reason distribution transformers are strategically placed relatively close to a group of consumers. This is why the transformer you see in your neighborhood is not randomly placed. Its location is part of distribution system design. What happens if something goes wrong? Everything sounds good so far, but an electrical engineer should never ask only how does it work. We must also think about what happens when it fails. Suppose insulation inside the system fails, or two conductors accidentally make contact, or some other short circuit condition develops. What happens to current? Remember, I is equal to V divided by Z. During a short circuit, the effective impedance may become very small. Therefore, if the impedance value decreases, the current will increase potentially very rapidly. The large fault current can damage transformer windings, conductors, insulation, connectors, and surrounding equipment. So the system requires protection and isolation. Depending on the particular distribution arrangement, engineers may use devices such as fuse or fuse cutout, switching isolation device, circuit breaker or recloser, and related protective equipment. Now imagine a thunderstorm. Everything is operating normally. Suddenly lightning. A lightning event nearby can create a severe transient overvoltage. Now ask yourself, the transformer is already designed to operate at thousands of volts, so why should it be afraid of lightning? Because the problem is not simply high voltage, the problem is an abnormal transient voltage that may greatly exceed the normal insulation stress for which the equipment is intended, that can damage the insulation. So distribution systems commonly employ surge arresters near vulnerable equipment. Conceptually, the normal voltage means arrestor has little influence, but during a dangerous surge arresters conducts or divert surge current on earth and helps limit the voltage appearing across protective equipment. A simple analogy is pressure relief mechanism. When everything is normal, it does almost nothing. When an abnormal condition occurs, it provides an emergency path. Why does electricity need earth? That raises another important question. Pause and think. Why do we need earthing? Are we simply throwing useful electricity into the soil? No. Under normal operating conditions, the purpose is not to waste useful power into the ground. Grounding or earthing can serve several important functions depending on the system, including safety, voltage reference, fault current paths, surge current paths, and supporting correct protective device operation. Imagine a metal enclosure that should normally be safe to touch. Now suppose insulation fails and an energized conductor conducts the metal. Without an appropriate protection and grounding arrangement, the metal could remain at a dangerous potential. Therefore, grounding and protective systems are designed so that the abnormal conditions can be managed and disconnected appropriately. This gives us one of the most important lessons in EEE. A good engineer does not only design a system to work, a good engineer also considers how it will fail safely. Why are power conductors usually higher? Look at this arrangement. Why is higher voltage equipment generally kept high above normal human access? Think like an engineer. Why not install the medium voltage equipment only 2 meters above the ground so maintenance become easier? Because convenience is not the first priority, safety is. Higher voltage system require appropriate face-to-face clearance, face-to-earth clearance, insulation level, conductor spacing, and physical separation from people and other services. So, the physical position of the equipment is also part of electrical engineering design. What about all those messy black cables? Okay, now let's return to perhaps the most visually obvious part of this photograph. Look at this huge bundle. Are there really hundreds of power conductors running through this single pole? Not necessarily. Many lower bundle cables on urban poles can belong to communication service such as internet, telephone, fiber optics, cable television, or other communication system, and this gives us another beautiful EEE connection. Electrical engineering isn't only about power. A power conductor and a fiber optic cable may physically share the same urban infrastructure, but they perform completely different jobs. A power conductor transfers electrical energy, while an optical fiber primarily transfers information using light. From the ground, both may simply look like black cables, but an engineer learns to see function, not only appearance. Now, connect this pole to your ceiling fan. Imagine you are sitting inside the nearby building, you feel hot, you reach the switch, the ceiling fan begins rotating. Simple? Not really. The fan requires electrical power. That power is supplied through the building wiring. The building receives power from the local low voltage distribution system. That system receives energy through a distribution transformer. The transformer draws corresponding power from the medium voltage network. The distribution feeder receives power from an upstream substation, and the substation is the part of the larger electrical grid. So, one small action when you click on this switch connects you electrically to an enormous interconnected system. Conceptually, generating station, then transmission network, substation, distribution feeder, distribution transformer, low voltage distribution, your building, then switch, and finally fan, right? So when your fan starts rotating, the wall socket is not the source of electrical energy. It is simply one of the final connection points in a much larger power system. Now, how electricity reaches a fan? Before we get into the details, let's understand how electricity actually reaches the fan in our building. If we look at this picture, the whole process starts at the generation station. This is where electrical energy is produced using generators. From the generating station, the electricity enters the transmission network. You can see the large transmission towers in this picture. Electricity is transmitted at a very high voltage because higher voltage allows us to transfer large amount of power over long distance with lower power losses. Next, the electricity reaches at the substation. At the substation, transformer reduces the voltage from the high transmission level to a level that can be used by the distribution system. The substation also contains switching and protection equipment to safety control of the power system. From the substation, electricity travels through the distribution feeder. These are the lines that carry electrical power toward different neighborhoods, commercial areas, and buildings. As we get closer to the customer, we have a distribution transformer. You have probably seen transformers like the mounted or utility poles in residential areas. Its job is to step the distribution voltage down to the low voltage required by the customer. From this transformer, we have the low voltage distribution system which supplies electricity to our building. Now, once the electricity enters the building, it passes through the electrical service and panel and is distributed to different circuits. For example, let's consider this fan. There is a switch connected in the fan circuit. When I turn the switch on, I close the electrical circuit. Current can flow through the circuit to the fan motor and the fan starts rotating. When I turn off the switch, I open the circuit. The current stops flowing to the fan and the fan stops. So even though turning on a fan looks like very simple action, there is actually complete electrical power system behind it. The power travels from the generating station through the transmission network to the substation, through the distribution feeder and distribution transformer into our building, through the switch, and finally to the fan. And this complete journey is very important to understand because in the next part, we can start looking at what actually happens electrically when we turn that switch on. Before we finish, let me ask you something very interesting. Which is dangerous, voltage or current? Some students immediately answer current, others say voltage, but an engineer should be more careful. The hazard is associated with current through the body, but the current that can flow depends on voltage, body impedance, contact conditions, current path, duration of exposure, frequency, and other factors. The simplest relation is I is equal to V divided by R. So, voltage and current cannot simply be separated when discussing electrical shock hazards. Never approach, touch, climb, or attempt to inspect distribution equipment closely for the purpose of identifying components. Medium voltage equipment can be lethal even when there is no visible spark, sound, or obvious indication of danger. Observe electrical distribution equipment only for a safe location. Now let's go back to the exact same picture that we looked at the beginning of this video. Nothing in this picture has changed, but hopefully the way you look at it has. At the beginning, if you were not familiar with power system, you might have looked at this picture and simply thought a pole and some wires. But honestly, that would be a perfectly reasonable first impression. But now, let's look at this picture again. First, look at the conductors. Before this may have looked like just wires running from one place to another, but now you know that their position matters. The distance between conductors, the distance from energized conductors to ground structures, and the distance from the conductors to surrounding objects are all important. So now when you see spacing, you should think starting electrical clearance. These conductors cannot simply be placed wherever we want. Their spacing has to help prevent an electrical arc from jumping between phases or from an energized conductor to ground. Now look at these ribbed components. These are the insulators. Their job is not only to mechanically support the energized conductors, they also electrically separate those conductors from the grounded pole or structure. And notice that the surface is not smooth. Those ribs increase the distance that leakage current would have to travel along surface of the insulator. That should remind you one another concept, insulation and creepage distance. This becomes especially important when the surface is exposed to rain, dust, salt, pollution, or other contamination. Now look at this transformer equipment. This is where we should start thinking about voltage levels. The electricity traveling through the distribution system may be at a voltage that is much too high to use directly in a home or small commercial building. So the transformer changes the voltage from one level to another. Now instead of simply seeing a large piece of equipment mounted on a pole, you can recognize the function behind it, voltage transformation. In other words, you are beginning to see the system based on what each component actually does. Then look at this production equipment. A power system has to be designed with the assumption that faults can happen. A conductor can contact another conductor. Equipment insulation can fail. A tree branch, animal, or damaged component can create an abnormal electrical condition. When that happens, we do not want the fault current to flow continuously. Production equipment helps detect or interrupt abnormal conditions and isolate the affected part of the system. Now, when you recognize device associated with production, you should think fault protection. What about lightning? Remember, these conductors and pieces of equipment are outdoors. They may be exposed to lightning and other transient overvoltage. A very short voltage surge can produce an extremely high voltage that may damage insulation or connected equipment. That is why surge protection devices are used. So even if lightning itself is not visible in this photograph, the system should make you think about surge protection. Now think about the connection to earth. Not every important part of this system is up in the air. Grounding provides an intentional electrical connection to earth and plays an important role in system operation and safety. It helps establish reference potential and provides paths for certain fault and surge currents. So when you look at the pole now, you should always be thinking, where is the grounding conductor? What equipment is bonded, and how is this structure connected to earth? That gives us another major idea, grounding and safety. Finally, look at these lower cables. At the beginning of this video, you might have assumed that everywhere on a utility pole carries electrical power. But now you know that is not necessarily true. Some lower cables may belong to communication systems such as telephone, cable television, or fiber optic networks. So instead of automatically calling everything a power line, you should stop and think power or communication. Their location, construction, attachment, and surroundings equipment can give us clues about this purpose. Now the photograph is exactly the same, the pole is same, the wires are same, equipment is also same. What changed is what you able to see in it. Now you are starting to see a system. You can look at the conductor spacing and think about electrical clearance. You can look at the insulator and think about insulation and creepage distance. You can recognize the transformer and understand why voltage transformation is necessary. You can definitely identify production equipment and think about what happens when a fault occurs. You understand about lighting and understand why such protection is necessary. You can look for grounding and connect it with both electrical behavior and safety. You can recognize that not every cable on a utility pole necessarily carries electrical power. Most importantly, these are no longer separate ideas. They are connected. The conductors, insulators, transformer, protection, surge protection, grounding, and communication infrastructure all have different jobs, but they exist together in the same physical system. And that is really the goal of this video. Not simply memorize the names of the components, but to look at an electrical distribution system and begin to understand why it is built the way it is. Electrical energy needs to reach consumers efficiently. For a given power, we know P is equal to VI. Increasing the distribution voltage allows current to be reduced. Lower current helps reduce I2R losses, but consumers cannot directly use medium voltage electricity. Therefore, distribution transformer steps the voltage down near consumers. Conductors must remain electrically separated. Therefore, we need clearance and insulation. The equipment must survive rain, pollution, and moisture. Therefore, insulators, geometry, and creepage distance matter. Faults can occur. That's why we need protection. Lighting and switching can produce dangerous overvoltage. For that reason, we need surge protection. Abnormal currents and voltage must be safely managed. Therefore, we need earthing or grounding. And around all of this, communication system may share the same urban infrastructure. So this photograph contains the power, voltage, current, electromagnetic induction, transformer, insulation, protection, earthing, communication, and electrical safety. This is why I always tell EEE students, don't study electrical engineering only inside a textbook. Look around you. Your city is full of electrical engineering. Before we finish, I want you to look at this electric pole one more time. At the beginning of this video, we saw a pole, some wires, a transformer, and lots of cables, but now we can see completely different. When you learn an equation, think what does this equation physically mean? When you see electrical equipment, consider what theory explains why this equipment works, and when you learn a theory, ask where can I see this happening in real life? Because engineering is not only theory, it is not only mathematics, and it is not only practical work. Engineering happens when we connect them: theory, mathematics, observation, and practical applications. That is engineering. So from now on, when you see a transformer, a motor, transmission tower, substation, charger, or even something as ordinary as this electric pole, just don't look at this. Think, what is happening here? Why is it designed this way? How does it work? What equation explains it? And what happens if something goes wrong? Think like an engineer, because when you start connecting what you learn in the classroom with what you see in the real world, you are no longer studying electrical engineering only to pass an examination. You are learning to understand the engineering happening all around you, and that is how you begin to think like engineer. So I want to leave you with a challenge. Tomorrow when you walk outside and see an electric pole, don't simply walk past it. Look at it from a safe distance and think, why is that conductor there? Why is that insulator shaped like that? Where is the electricity coming from? Why is that equipment installed here? Where it is going, and what protects the system if something goes wrong? Because the moment you start asking what, why, and how about the electrical systems around you, you stop studying EEE only for an examination. You start thinking like an electrical engineer. If this video helped you see an ordinary electric pole differently, then the next time you see electrical equipment around you, stop for a moment from a safe distance and think, what engineering is hiding here. Actually, engineering is not only about equations, theories, or examination marks. It is about learning to see the world differently. Where others see a pole and somewhere, you should begin to see a complete system. Be curious, always ask questions, why, how, connect what you learn in the classroom with what you see around you every day. Do not be afraid of difficult equations. Every equation you understand gives you another tool to understand the real world. Do not study only to remember, study to understand, study to connect so that one day when you face a real problem, you can use your knowledge to create a real solution. Observe, question, learn, connect, and create. Don't just study engineering, learn to think like an engineer.